But soon after came this long AI winter. And why did this winter happen? Because these rapid advances led to a hype of artificial intelligence similar to the buzz around deep learning today, or deep learning just after 2015, right? After AlexNet. And researchers made these large promises, these big promises to solve AI, received a lot of funding. But in the 70s, it became clear that those promises could not be kept, and funding was cut dramatically. And the field of artificial intelligence almost dropped to this near pseudoscience status, and research became very difficult. Very little funding, publications almost never made it through peer review, and PhD students did not want to work on this kind of problems, and these researchers were very lonely. And further advancements such as SVM, support vector machines, with nice properties in terms of training, provable error bounds, were preferred and took the front seat. However, a handful of researchers continued further down this path. I have written my views on it, how I have seen the winter myself after 2015, right? And this was not the major winter. The major winter happened before that. And I recommend you to read this. It's on LinkedIn. It's also on X, right? So LinkedIn and X, you can just Google for this and I'm sure you'll find it. I wrote this last year in September. And I'll tell you my story, right? So, handful of researchers, for example, Jan, nobody wanted to work with Jan. When I joined NYU, this was before AlexNet, Jan was not even famous. Nobody wanted to work with him because he was not publishing papers in the top conferences such as NeurIPS and CVPR. I happened to work with him because he was my next door office neighbor. My advisor said, okay, I am doing something else. Are you interested in working with somebody like Jan? And I was like, yeah, let's do it and let's see. And, I got lucky. I was at the right place at the right time. But immense respect for people like Hinton, for Jan and Bengio, who persisted tens of years of believing in themselves when the whole world was against them. And this is the reason why all these three got the 2018 I think or 17 Turing Award. And then of course Hinton also got the Nobel Prize last year and in physics. And then there are also Bengio, as you may know, is from the University of Montreal. Jan is still associated with NYU. Hinton was with Toronto, but now recently with Google, and now I think he's moved on since then. Schmidhuber is a little bit bitter about all these because he didn't get the award and the recognition that others got. But he was also one of those who persisted, and I attribute him only to LSTMs. But if you read his posts, he seems to have invented everything, all the way from CNNs to RNNs to transformers. But then, huge respect to this man, Andrew Ng. He was a professor at Stanford, behind Baidu's team, behind Coursera, and he's one of the best teachers in my opinion. A lot of you may have seen his deep learning course. If not, I recommend you to look at it. He also focuses a lot on intuition, and I think I like his style and way of teaching a lot. So these were people who persisted even when the whole world was against them, when nobody wanted to accept their papers, when no PhD student wanted to work with them, when they had little to no funding. But they persisted, and because of which they reaped the rewards of what were to follow. Yeah, but it is very difficult to kind of be in the shoes which they were, right? Like to kind of have gone through what they did. So this is why I have immense respect for them, because I've seen this up close. And then my life, along with all their lives, changed in 2013 because of this tipping point, because of this ImageNet competition, because of this paper from Alex Krzyzewski called AlexNet, right? So AlexNet was this paper on ImageNet classification with deep convolutional neural networks. Alex Krzyzewski, Ilya Sutskever, Jeffrey Hinton. And this was for the first time this deep learning based method beat all baseline methods, and by a big margin, right? So I'll show you later, but this is where it became very quickly clear that the other methods will not be able to catch up, and it is time to kind of give deep learning the attention that it deserves. And as you know, ImageNet is a data set with 1 million training images over 1,000 categories. So what happened during this tipping point? The reported error was 15.4%, top 5 error rate. What does it mean, top 5 error rate? You get the model to give you 5 predictions, right? The top 5 predictions. And if any of them is correct, if any of the classes of the top 5 is correct, let's say you have, say, a picture of a dog and you output, cat, dog, horse, table, and ball, right? But since the second one is dog, you still call it correct. And if you using such a method, they could get 15.4%. The next best entry, which was a non-deep learning based entry that year in 2012, got 26.2%. And then, of course, this paper got lots of citations. By 2018, 8,000. By 2019, like 2018, 19,000. And this is not today. This is when I was teaching at IIT Bombay. So this was like 2019. But today it has more than, 100,000, 200,000 citations. And this was the coming out party for CNNs in the computer vision community, but not just the computer vision community, in all communities in general. It shocked the computer vision community because it was trained on this end-to-end model on raw pixels. Back in the day, we were not training on raw pixels. We were creating these handcrafted descriptors, these handcrafted features on top of these pixels, and then training our SVMs, our boosted classifiers on top of these handcrafted features. And from here, it was apparent that deep learning would take over not just the computer vision community, but all communities, all machine learning, and other methods will not be able to catch up. So this is what happened in ImageNet 2012. This was AlexNet. And as you see, AlexNet has this big gap with all these traditional CV-based methods. In 2013, still some traditional, let's say, deep learning methods tried because they were still not on this bandwagon of deep learning, but then they did not do as well as the CV methods. But 2014 onwards, nobody even tried, right? It was very clear that deep learning is the way to go, and we should not do these handcrafted features. After computer vision, speech recognition was the first wicket to fall. Why? Because speech is very similar to, this dense signals, 1D signals instead of 2D. And then came NLP. NLP is a discrete, it's a sequential problem, and so on. So then it was NLP, RL, and so on. And it was when, why did this all happen? Like, what changed since the 70s? We still had these deep learning based models. We still had people like Jan doing LayNet. What changed? What suddenly happened that we were able to get to where we are today? So what happened was we got this large amounts of labeled text data for supervised learning. And this was from Fei-Fei Li. Right? Fei-Fei Li was a professor at Stanford, and she put a lot of effort behind collecting and labeling this huge data set, these 1 million data set image, right? So 1 million images in the training set and 100,000 in the test set, right? 200,000 in the test set. So this was the first, right? So the first was the data set. The second was compute. We had these giant graphics cards which could then kind of do a lot of compute because these methods were very compute intensive. In 2012, in 2011, we started to have these giant GPUs which could give us the compute that we needed to train these giant models. And lastly, algorithmic improvements such as ReLU, because it could help us train these deep models, these models where we were earlier getting these vanishing gradient problems, right? So if you remember, we spoke about vanishing gradients. So we then did not have these vanishing gradient problems, and also other methods such as dropout, etc., where with which we could kind of train these giant models without overfitting. Yeah. So these are the three things, in my opinion, that changed: data set, compute, and a little bit of algorithms. And then we ushered in this world where there was this one net, one model, right, to rule them all. It was not really one model which could do everything, but one kind of a network, one kind of an algorithm which could do it all. It could do all the way from protein folding to robotics to gaming, right, to things like Go, AlphaGo, etc. And deep learning became synonymous with AI. Anything where there was artificial intelligence, it was deep learning. And previously, problems which we thought were unsolvable became solvable. And this is where my life also personally changed. Because earlier, I was kind of identifying myself as a computer vision person. But from here, I became a generic machine learning person. Because once you're at the embedding level, right, once you have created, let's say, the feature descriptor, the lower dimensional representation of your higher dimensional paragraph, speech signal, image, whatever have you, you can then, it's all the same from there. You can even have embeddings in the same space. You can align your speech and text. You can align your text and image like we do in clip and blip and so on, right? So this is where we kind of could kind of become general, and we could solve any problem because deep learning was not limited only to computer vision, and you could do anything. By the way, here it's a malaria parasite being attacked by our immune system. So this is what AlphaFold is looking at here. So before deep learning, how were people doing it? There was still machine learning, right? So like your support vector machines, your SVMs, your boosted algorithms and so on. So what you needed to do, let's say you are interested in this game of football, right? And what you want to do is you want to, let's say, identify where the ball is. And so for that, you want to train an object detector for, say, detecting the football. And to do that, what you would do is you would hire a bunch of these traditional computer vision experts, and then they would craft these handcrafted features, these handcrafted descriptors. One of them was called SIFT, SIFT, right? SIFT stands for Scale Invariant Feature Transform. There was the other one called HOG, histogram of gradients, where they did things like create a histogram over the orientations of gradients within a patch of the image. Yeah, so these were very handcrafted, and you did not look at, let's say, the raw pixel, because it was very hard, because these models like the SVM, they could not train on those raw pixel. It was too, let's say, difficult. So they needed a lower dimensional representation, this latent space that we talk about, but they were all handcrafted earlier. But then post deep learning, what we needed to do was, let's say we were doing object detection, we would just throw a deep learning model on top of it, along with a lot of data and compute. And this is where the whole paradigm shifted to this data-driven method, this data-driven paradigm, which we spoke about in the very first week. So I think it's an incredible time we live in, and I'm super excited about the future, and I'm sure you are as well. Thank you.